Welcome to the new video of this series where we are looking at model predictive control, specifically linear model predictive control in MATLAB. So we have already seen a few examples, and in this video we will look at how to put constraints on the control variable. So we're talking about the output variable in this case, okay? So I will not explain the system again, because we have already seen it. So if you have seen the previous videos, you should be fine. So we will run the same commands. So let's start by setting the parameters, then creating the state space model. Then here we create the MPC object. Okay, for now is exactly the same. And we are putting constraints that we know will not do anything to the output variable, because if you remember, the set point is 1. So here we're just constraining it between -2 and 2. But we will see then a few examples with different numbers, okay, different limits. Okay, so let's run this. Now we will skip what we've done last time. This was the constraints on the control effort, which we have seen in the previous video. And now we want to focus on constraints on the position, which in this case is the output variable. Again, I will not go through this code, because it's exactly the same of what you've seen last time with the manipulated variables. So the differences are the numbers here. This matrix is called OV constraints, then the labels are different, but it's basically the same. The only difference is the main difference, really the important difference, is that this part here we set maximum and minimum of the OV field in the MPC object. And this is exactly what we want to do. This is the constraints that we're putting on. And we pick them from this structure here that we loop over in the same way we did last time. Okay, so let's look what happens if we run this. Okay, so it did run okay. And it produces this figure. Maybe let's just quickly look. Here there is a plot function, a bit of code to generate the figure that we are going to look at now. Okay, again, the important thing is not this code. Now we want to see it. We want to see the result and the behavior. Okay, so the magenta response is with a constraint of 1.15 meters, which essentially is beyond the natural overshoot that we were having before. So with this cost function and these weights and this configuration, we don't exceed 1.15 meters. So the MPC doesn't change its behavior, okay? And what we see here with the magenta response here and the magenta response of the control effort is exactly the same response we had in the other example, when the constraints on the control effort were ±10. And here we have always ±10 as constraints on the control effort. Okay, so that's one. Then we will zoom bit more vertically here, which is where we are interested. And then we can see that in the second case, where we have put 1.05 meters as a maximum value that we want the position to go, we see that the MPC changes its response, and you can see it in the bluish, light blue color here. So on the output variable, we just touch on the constraint, but we don't exceed it. And the same color here, the light blue control effort here, the force, has a different shape respect to the magenta, right? So it's a bit more cautious, we could say. It starts breaking earlier and then it pushes less afterwards, okay? So it minimizes the risk of overshooting beyond our constraint. Then we can see the green response, which is again an even stricter constraint, which goes to 1.02 meters. And I think what's important here is we are asking for a very fine response, because we are asking it to go to 1 meter as a set point without exceeding fundamentally 1.02 meters. So it's very strict as a movement, and it's very strict as a constraint. And again, we see that the response, the green, touches barely the constraint, and then it plateaus back to our set point. Same thing, looking at the green here, the control effort, we see that again this is even more cautious as a control, as a manipulated variable, as a control input, because it starts breaking, it breaks harder, reduces the force earlier and more, and then it doesn't push as much as the other two responses, which is all expected, but I think it's very interesting to see how it manages. What is important is, of course, that this is a simulation, and even more importantly, the MPC algorithm here knows perfectly the plant, right? So we are telling a certain plant model to the MPC, and we are simulating it on that exact plant model. So it's super easy for the algorithm fundamentally to obtain this result, because it knows exactly what the system is going to do. Nevertheless, it's not so easy to do the same thing with other techniques. So once again, MPC excels with constraints. Thank you very much for watching.